Welcome back, guys, to the Women in Code Python LeetCode study group. My name is Karen. I'm the moderator today, and I am with Chethana, who is the instructor, amazing instructor for this series. Chethana, off you go.
Thank you so much, Karen. Before everything, I just wanted to answer Gloria's question real quick. So this would be we still have one more session after this. So today's session and that session, it's mostly like the past 7 sessions we had like streamlined, like we took one pattern and we solved something with it. These 2 sessions would just be like, okay, what else is there? Like, is there something else we missed? Is there something else we just want to introduce and then see like where we go on with that? And after this, that would be our last session. The next one would be our last session. And then if you want to keep the ball rolling and, work with other kinds of problems, maybe you could start posting in the LeetCode study group. I think Karen and I, we wanted to sync up after the sessions to see how we can keep it going, because like we have a lot of, all of us have work and stuff like that. So it's just been like super busy. So we're gonna have to like sync up after that and do it. Yeah, so with that, I'm gonna start talking about our agenda today, and then we'll see where it goes. Okay, so what have we seen so far, right? Like just like a brief, okay, we've done all this, that kind of thing. And then we're going to talk about 2 additional patterns today. The first one is iterative tree traversal. We're going to briefly introduce it, briefly talk about 2 problems and how do we approach them, and like just some examples. We're not going to code them out, the first 2. And then we're going to talk about fast and slow pointers, just again an introduction, and then we're going to code this one out. It's a problem called linked list cycle. It's a fun problem actually. We'll get to that. And yeah, and then we'll wrap up with some questions. You could also ask questions throughout the session along the way. I check chat now and then, and Karen does as well, Stephanie, everybody. So yeah, feel free to post them in. Okay, I don't know why I had to put this slide, but it seemed super dramatic, so I just added that in. So, okay. What have we done so far? We started with 2 pointers. We went to the sliding window approach, binary search, greedy approach, hash tables, DFS and BFS, backtracking. So all of this, and then Stephanie posts all of our videos and stuff within the channels, and you could check that out there. You could also click on this playlist, and like this is the whole LeetCode like study group playlist so far. So if you want to check that out, you could do that. Okay, what now, right? We're just going to, this is a bonus patterns kind of session, right? I didn't like, when I initially started this, in all honesty, I didn't have any like fixed plan for the last 2 sessions. I just thought, let's see how comfortable everybody is, and we'll try to see what to add in or not. Okay, so let's start with the first one. Iterative tree traversal. So far, we've done tree traversals. Like generally, when somebody says, "Okay, let's talk about trees," not the data structure trees, but so when you talk about trees, you think about it being a recursive data structure. Like you don't. As for me, basically, when I started, I didn't think of it as something you could sort of look at level by level or step by step. When you look at an array, you see, okay, our position is here. When we move to the next position, it's a +1 or like something like that. You just move that way. And with something like a tree, it just feels that anytime somebody says, okay, let's see an Inorder tree traversal or something like that, we would usually just go into our recursive mind state and we'd solve it that way. that is good. It's really, it's intuitive, but when you solve it iteratively, using a stack specifically, if you're doing a depth first search, the same recursive stack you're going to sort of implement here, like in your own way. And then if you do your BFS with a queue, how are you going to do it? We're just going to briefly touch upon that and see how fun it is to do things that way. Because for me, only when I started doing trees iteratively did I actually like the tree data structure. Other than that, like I've always been very super skeptical about it. but yeah, okay. So that's the what. The why is, like I was saying, right? Like recursion, sometimes with recursion, you just say, okay, like go, base condition. Once you hit that, go back, return answers for the previous ones, because those function calls would be wrapped inside your, like in your call stack, right? So return those answers, bubble back up, and then return your final answer, something like that. Oh, sorry, I should have, okay. So a DFS is a depth first search and BFS is breadth first search. I'm gonna make that change in the slides later. Really sorry about that. So let's see, okay. Where was I again? Okay, so seeing how these two depth first search and breadth first search are done, it sort of, once you keep doing it, you sort of unlock newer patterns, and you'd understand. I can't really explain it in one session, but like as you go on, you definitely, you have my word for it, because it actually happened to me. So okay, so with the okay, for promise for this specific like depth first search and breadth first search, I'll just briefly talk to you about it. You could also look at it in depth in one of our previous sessions. We literally, like, we went through everything about it, but basically there are two types of ways you could traverse or you could search within a data structure. Like it could be a tree, it could be a graph, like so on and so forth. So for some more, thanks Stephanie. Yeah, so once you look at that playlist, you'd I mean that video, you maybe understand more about it. So awesome. Yeah, let's now, just a brief introduction again. Let's just go into two problems that I really like when it comes to iterative depth first search and iterative breadth first search. Okay. My pointer. Validate binary search tree. The link to the problem is in here, and let's basically just read the problem. I've basically posted whatever is on the problem here. So given the root of a binary tree, determine if it is a valid binary search tree, which is BST. And what do you call as BST? There are these three conditions that you'll always see when it comes to a binary search tree, right? We'll look at an example after the slide. But like, if you're familiar with a tree data structure, you'd understand that you'd have a node, and then you'd have a left child, left or right for you, but you would have two children, like left and right. And sometimes you may not, but in case of a binary search tree, how it's going to be is whatever is on the left, every node that's on the left of your root, it has to be lesser than your root, which is the first condition. Oh, wow, okay. The left subtree of a node contains only nodes with keys lesser than the node's key. When they say key, they mean the value of the node. Okay, and the right subtree, this is the left subtree. When you look at the right subtree, all of it should be greater than the node. Okay, so these two are super important conditions when you're doing a binary search tree, or when you're looking at it. or when you're just doing a tree. And both your left and right subtrees must also be binary search trees. What does that mean? You bubble down all the way till the end, and if you have maybe one node and then a lot of nodes on the left and then a lot of nodes on the right, they should also follow the binary search tree principles or rules. Only then can you call the entire tree a binary search tree. I should stop moving my hands and go into some examples. Okay. Yeah, so our problem is basically, if you're given a tree, a root of a tree, check if that is a valid binary search tree or not. If it is, you return true. If it's not, then you return false. Okay, so let's look at a couple of examples. Again, if you've been here for previous sessions, this session is going to be a little bit different because we're just touching on a few patterns and then continuing to two patterns, for example. But yeah, so if you look at this, these are two trees, right? The first one, these are directly from LeetCode, like this problem's description. If you go into it, these are literally from there. Okay, so the first one, it has 3 nodes in total, and the second one has these many nodes. So these are 2 separate trees. How do you, which one is the valid binary search tree? I don't understand what LC, Rajeshi, can you elaborate what you mean? Oh, okay. The question, Stephanie, could you drop the link to the question? This is the problem, basically the problem in LeetCode. So if you, I'm gonna actually drop in the next one when we get to that. But yeah. Okay, so sorry about. Okay. The sorry, I'm gonna scroll up to see. Rosa says 1. Promises 2. Do we understand what like binary search trees? If you feel comfortable so far, just drop a B or something like that, or a thumbs up in the chat so that we can discuss more. Awesome. Okay, so I'm gonna wait for like maybe a couple more seconds to see if there are more thumbs ups or not, because I'm not sure how to gauge the situation. Okay, that's better. 4, yeah. Okay, so let's see which one's a binary search tree and which one isn't, right? So we had 1 is the binary search tree, 1 is a valid binary search tree, and we had another answer saying 2. Like if let's break it down to see which one it can be. 3 conditions, right? The first one was left subtree 1. In this case, there's just 1 tree, like there's no subtrees for the first example. So the left subtree should be lesser than this left subtree's values. That should be lesser than the node, and then the right subtree's key or value should be greater than the node. So if you look at this, there's no additional subtrees or anything like that. Seems plain enough. The third condition doesn't really apply here because there's no subtrees. And so this is a valid binary search tree because 1 is lesser than 2 and 3 is greater than 2. There's no equal to or anything like that, right? So the first one's the valid binary search tree. Let's also unpack what's happening in the second one to understand. 5 is the root of the tree, and 1 is there's no additional subtrees there. So one is just the one is the left subtree, and then this whole 4, 3, 6, they form the right subtree of 5, right? So let's look at all our elements on the left subtree of 5. So 1 is definitely lesser than 5. So the first condition is fine. Let's look at the second condition, right? 3 conditions. The first one was left subtree. The value of the left subtree, it should be lesser than the node's value. And then second one was the right subtrees should be greater than, should all, whatever is within it as well, should be greater than the node's value, if you look at it in that way. And then the third one is literally like, they should all be binary search trees, which means if you think of it like from an entire perspective, from the roots perspective alone, it means that everything to the left of it should be lesser than it, everything to the right of it should be greater than it. But when you go into the subtrees, for example, 4, if you see 4, what is on the left of it? 3. And is 3 is lesser than 4, right? But it is also lesser than 5. But we have a condition saying that everything that's on the right should be greater than 5. So for example, if we had 6 or something instead of 4, right? And then we had 4 here, then then we had let's say 7, and then we have 6, whatever. Basically what I'm saying is anything that's on that end, anything that's on the right side should be greater. That's it. And then if you look at it here, in the context of 4, 3, 6, this is a valid binary search tree, right? Because 3 is lesser than 4, 6 is greater than 4, which is what we want. But when you look at it in terms of the root, this like 3 is not greater than 5. 3 should have been greater than 5, and if so, then and even 4 is also not greater than 5. So the second one doesn't make a valid binary search tree. Okay, so far so good, right? We sort of figured out some ideas of how we can debug our input to figure out an output. So how can we actually solve this, right? If we're given a tree with the conditions, we could do, okay, here, we could do it like that. But if we're given like 100 node tree or something like that, then we're gonna be stuck, right? We're gonna we're gonna like, it's like you need to look at individual subtrees. If you look at only the root, then we could do it easily. But if you're going to do individual subtrees and like bubble up those answers and stuff, then it's going to be a bit difficult. So how do we actually do this? Let's try, because in general, if you have trees or anything, like, first of all, like your mind should be wired to try out all of those traversals. You just like be like, okay, let's go over this and see if there's a pattern we can find to solve this problem. So there is a pattern, and we'll understand why that works. So let's try doing an in-order traversal on both. And what does an in-order traversal mean? You start off with your left subtrees fully, and then even within that, you start off with your left. Like, if you basically, if you have a subtree within the left side, you would go all the way till the leftmost leaf node. Leaf nodes are the nodes right at the end. Like, for example, 3 and 6 here are leaf nodes, 1 and 3 here are leaf nodes. So you would go all the way till the leftmost leaf node, and then that would be where you start. So left, and then what is the node there? You'd go to that, and then right, and you do the same thing. So basically left fully, and then the node, and then right. That's how you'd visit it in order. And an easy way that Oh, okay. Like, yeah, I'll get to that in just a second. I'll explain what this 1 and 2 mean in a second. But sometimes when somebody says in order, they like, when I used to like study about it before, it's easy to remember, like when you're reading the letters of the English alphabet in a book, right? You start from left to right. You left to right. If you're obviously if you're looking at other scripts like Arabic or like if you're reading a manga or something, it's going to be different. But for English, you're going to go from left to right. So in order, right? So that's a good mnemonic that I used to use before to remember. But yeah, and let's talk about like what these traversals, like why we have 1 and 2 here. The first one is the first tree's traversal. You're going to start off with your left node and right. So 1 is your leftmost node, and then you'd have 2, and then you'd have 3. 1 goes into the left subtree situation, so 1, and then 2 is the actual node, and 3 is the right subtree of your node. So 1, 2, 3. So that's what you have. That's what I have here for the first one. And then for the second one, you start off. Can you explain why? Yeah. Okay. Yeah. Oh, yeah. I'll get to that. Okay. So again, left subtree, right? So that's 1, and then node, great. And then now you're going to the right subtree. This is where we get like an issue here, right? But even within this, you would have to go, because this is in order, you again have to start from your left, and then you have to go back to your node, and then you have to do your right. Even within the subtrees, you're going to have to do that. So yeah, so you do 3, you do 4, and then you do 6, and then you're done, right? So these are the 2 traversals that you have. What difference do we see here in these traversals? Like, this is an array, like plain as day, it looks like an array, like in our mind from what we see here. So what difference do you folks see in 1 and 2? I'm gonna take a quick second to see what responses we get. Within the traversal arrays alone, nothing to do with the actual tree, just those 2 arrays, 1 and 2. Look at them as 2 separate arrays. It's very subtle. I should have taken a bigger data set, but I mean a bigger tree. But what do you? Oh, okay. If you have another branch off of 3, then you'd go. Ooh, wow. Then you'd go all the way to the left side of that branch of 3. If you have some other node, some other value that's greater, I don't know, 7 or something, it's not going to be a valid binary search tree, but still, like you would go all the way to the left, and then you would backtrack. You would go to the node, and then you do the right for that, and then if you do that, that means you finish the left subtree of that particular like branch, right? And then you'd go to the node again, and then you do the same thing. Even for the right subtrees, they would also have left subtrees within them, right? So you would traverse all the way to the end, to that leftmost leaf node within that particular subtree. So whichever subtree you're looking, you go all the way to the left, and then you would go to the node, and then you would do the right. But yeah, so I'm gonna move quickly now, because we have some more stuff to cover. The difference between this, like if you notice, the first one looks sorted, right? Like it's a very tiny like tree, but the elements, they're all they're in order, like 1, 2, 3, and there's no there constantly, like, they're increasing, and they're in ascending order. And if you look at this, it doesn't really have that. Like, if you have 1 5, suppose if you had maybe 7 or something like that, like 6 7, like anything greater than 5, and then anything else that comes after 7 should be greater than it as well. If you do that, then like then maybe that's sorted, right? Like, but from what we discussed before, we already saw that the first tree, which has the sorted array, it's like, it's a valid binary search tree, and the second one isn't. And you could literally do this with any tree that you want to. And you're going to, I chose these 2 specific examples because they're examples from LeetCode, and I thought, like, if you see this problem again later on, it may jog your memory. So that's the difference between them, right? So then it makes this simple. Like, if you just sort of go over the entire tree, and if you keep track of what is your, like, how do you generally do like a comparison, right? You'd be like, okay, if you have 1 5 3 4 6, you'd look at the current one, and you would make sure the current one is greater than your previous, right? So like, if you're at 5 right now, 5 should be greater than 1, and then whatever element comes after 5 should be greater than 5, and so on and so forth. So basically, just have like a previous pointer kind of situation, and then like a current pointer or something like that. How do we actually do this, right? Like, we're just talking here. And again, like, I won't be coding this out, but I have a snippet within here to explain this a little bit from what I was doing in LeetCode. Before that, let me look at the chat real quick. Oh yeah, I'm sorry, I seem to have missed some stuff in chat. Yeah, it's ordered. Yeah. Okay. Awesome. So yeah, many of you have already answered. So sorry, I missed that in chat. Let's actually look at this solution, right? Why are we like, we were just talking, we never actually like worked on it yet. If this were one of those previous sessions, like I would have done this on a REPL, but time's sake, and we have to cover 2 more, so we're just going to do it this way. But I will try to put these solutions into the REPL, so that you can there's a REPL if you're joining us for the first time. Usually we have all of our previous sessions and all of that, the coding solutions and stuff within a REPL, like it's like an online ID kind of thing. We have it within that, and we usually work out any problem within that. So for this session, I'm not using a REPL. I'm just talking about it and then continuing. We would have one more question that we wanted to do, but I'll be doing it directly in LeetCode and not in the REPL. Just wanted to say that quickly and move on. Okay. What is a solution, right? If you see this is the same tree that we were looking at before, and yeah. So if you look at the in order for it, we were talking about this, right? So 1 5 3 4 6. That's what I've written here. And how are we actually going to do it? Because we were thinking to go all the way down and then do it, right? So that is a depth first search. You go all the way down. You don't do, if it's a BFS, if it's a breadth first search. I'm sorry, I'm used to like saying BFS and DFS. I'm gonna like not abbreviate it. No. Oh wow. So yeah. So in this case, with the depth first search in general, you with recursion, you use a call stack. And that call stack, what it does is if you have a function call, like if you have the first function, maybe if you're calling like a lower order function, you would have the first call that would be pushed into your recursion stack. That would call another function call, and that would be pushed onto your recursion stack, sorry, call stack. And it would go on and on and on until you hit a base condition that just says, okay, return this thing, this value, right? Once it returns that value will be applied to whatever is on top of the call stack, right? A stack is always like first in, first out, right? So sorry, last in, first out. So whatever's on top, that would be popped out, and then you would like so on and so forth. It would keep going on until you reach the end of your call stack. So how do you stimulate this, or sorry, how do you simulate this in this question, right? You would basically create a stack. So that's what you're doing here. You're creating a stack, and then you're going to be doing like you're going to be going all the way till the end, till the leftmost leaf node, and then you would basically pop out from it, look at the previous value, compare, and all of that. I'll get to that in a second. So you're basically setting your current node to your root, and then before anything, your previous would be none. And while you have values in your stack, or while your current, this while current thing, it was a bit of a like when I was doing it, I was like, okay, while your stack exists, right? But you didn't really populate your stack at this point. You could and then do it, but yeah, I did it this way. So while these exist, you're going to go all the way till the leftmost leaf node. So what do you do during each of that, each of your iterations till then, right? You append whatever current value you have, whatever current node you're at, you're going to append it onto your stack one by one, just like it would happen within a call stack. You're going to like sort of slice out the left and right node situation. It's not exactly like a recursion, but yeah. So yeah, you would append your left nodes into your stack, and then once you hit the end, suppose you're at 1, right? If you're at 1, then there's no more, there's nothing more to push beyond that or append. So you'll basically, this while loop will stop and you'll come out of it. And now what you're going to do is, what you'll have is your stack will have whatever you see from the root until like the last leftmost leaf node. You'll have all of it in your stack. And so you're going to pop one by one, you're going to pop each of it. And then if you already have like a previous value, this is what we were seeing before, right? You're going to be comparing, if you have 1 and 5, you're going to be comparing, 1 would be your previous, 5 would be your current. So you'd compare 1 and 5. And if by any chance your previous value is greater than your current value, or like if you have a vice versa check for it, whatever. But if your previous value is greater than your current value, then that means that that means it's not a valid binary search tree, by like just because of what we've derived and what we've seen with this Inorder Traversal so far, right? So that's what I've written here. If you see that this condition fails, you straight away know that it's not a valid binary search tree, and then you return false. And then what you do is you would update your previous with your current, and then and then you already visited the left, right? And then you already saw the current node, like you checked the current node's value. So you're going to move to the right next. So your current would be currents next, and then again you'll do the same thing. You'll iterate all the way to your left node. The same thing will happen over and over again. And at the end, if you don't return false anywhere, right, which means you reached all of this, like you finished, in this case, like 1, 2, 3, you finished all of this and you didn't reach a situation where your previous was greater than your current, in that case, you would just in the end return true. And that's about it there. I will make sure to like just add this into the REPL, just so that you have some reference later on. But like this wouldn't work with like, you know, even if you're doing it in a REPL, you'd have to create a node, you'd have to like a node class, and then you would have to like create left and right children for the node, and like you'd basically have to set up a tree data structure if you're doing it with the REPL. So like I'll see if I can do that, or I'll just post the solution within there so you could try it out in LeetCode. Yeah, that's the first one. And then this is the I'm gonna take a slight short break, just a water break, so that like we can continue after this. Yeah.
All right. Thank you, Chethana. Let me just recap everyone who just first time joining in case you this is the first time and this is a bit hard to catch up because we've been running through the series. So this is how the structure is. So Chethana planned the problem, and then she will explain, we'll walk through the how you think, how to think the pattern, how to think the way to solve it, and then finally we'll write a code. So usually the code doesn't take too long, but then it's the structure thinking through that would be like it spends the most time. So like if we're doing on our own, that would the same as well. So just a little like Chethana said, we usually do it on REPL, but we do it on the LeetCode this time. So I just post a link for those of you who just joined in for the first time. We save all of the materials on the GitHub, which I just post. So you can find the notes here. You can find like all the slides from the previous session. I also attached the GitHub link and the REPL link as well. So those of you who don't have the REPL link, you can like also reference for the LeetCode link as well. So if you that's good. If you have any questions, we will share on us on Slack. I'll be probably uploading this section's material later on, maybe tomorrow for you guys. So just to give me a little time. But then like if you want to review the previous ones, like they are there.
Awesome. Thank you so much, Karen. Yeah, so the previous sessions, they're much more like I don't like to run through problems. Like if you see any of my previous sessions, I definitely don't like to just do what I did just now. But like I usually sit and do like examples and then approaches and like brute force and then what we can do. Oh, okay. Thinking of time complexity, I just want to quickly mention, like if you look at this here, like you have to visit all the nodes, right? Like that is definitely an O of N for sure. And then you would like in previous, I'm just trying to think about what I used to do before. And then in previous problems, you'd have to, I'd work through both, like if there's any weird time complexities that's like not too difficult, I mean not too easy to get, I used to like work out some of that. So this one's like a breeze through kind of session. Yeah, I'm gonna continue now. The next problem that we're going to be looking at real quickly is binary tree right side view. This is one of my this was the problem that actually gave me confidence to do tree problems. I always try to fit this pattern into like the pattern that we're going to talk about here, iterative breadth first search. I always try to fit it into any problem I see. I'm like, oh, okay, we could do it that way, and I try to do that. So let's talk about this problem really quickly. Given the root of a binary tree, imagine yourself standing on the right side of it. Return the nodes you see ordered from top to bottom. Okay, easy enough. You have a tree, and then you're standing to the right side of that tree, and then you're going to look up, right? And then you're going to you're going to return whatever nodes or whatever values you see from there. So basically, you're going to stand next to 4 on the side, and then top to bottom, right? So you're going to return 1, 3, 4. That's going to be your output. Okay, very simple. There's nothing more than that you have to think there. But like, how do we actually do this? You could do, there's like, for each of these problems, it's not just this one solution that's there. You could do the same thing. If I choose the DFS for one thing, you could do a BFS for it. Like you could do multiple things. You could, even for the previous one, recursive is fine. I did it that way. I liked that solution more because it was super intuitive. So really whatever floats your boat. But for the sake of the session, I really wanted to mention, try to like expose you to those patterns. For this one, if you do a DFS, it's still fine. It's just like, it doesn't seem intuitive to me because a DFS, you go all the way down. Here you seem to return whatever's at the end of it, right? Yeah. And if you look at this, you would just need to return 1, 3, and 4. So the last element of each level, that's what you need to return, right? Look at the levels here. Level 1 just has 1. Level 2 has 2 and 3. Level 3 has null, 5, null, and 4. I didn't include the nulls, but the valid elements are 5 and 4. So I've added that. Great. So what is from literally just going over these levels, what is the output, right? You're just going to look at the last one, 1, 3, and 4. That's it. Just going to, in each level, literally add each level to a queue, because this is a breadth first search, right? You're not doing a depth first. So you're going to add it to a queue, each of these levels. So the first one, 1, you'd add it to queue, and then you'd pop whatever you added, like whatever you added first, because this is a queue, first in, first out. So you would pop that out, you'd pop out 1, right? And you would visit its left and right children, right? So if, but before you visit its left and right children, if the current node you're on is already the last element of your level, right? How do you find out the level? The length of each level. If you have a queue, and if you, okay, I'm not going to go into implementation details. I'm going to do it in the next slide. But for now, let's just do it this way. We're going to take that node. We're going to visit its 2 left and right children. As you visit it, you're going to push it into the queue. And then if whatever your, and then like before you visit it, you would also check if that particular node is the last element in that level. How are we going to do it? We're going to see it in a second. But as and when you do it, if you're at the last element, then you're going to append it to your results list. And pretty much at the end, you just return your results list. Okay. Again, another like another snap of the code, but how we're just going to, whatever we spoke about in just a second before, we're going to be like looking at it once more, just because when you see things iteratively, they really make sense. Like even if what I say now doesn't really hit home, I really encourage you to like look at it again, or look at this video again, try to ignore all my hand movements. But if you see it again, if you see that code again, you'll understand better. So yeah, let's start by initializing our queue, right? Initially, what will be within our queue, like the first element that we're ever going to see, which is the root, right? So you're going to append that into your queue, and then result is just your result. And while you have while there's at least one element within that queue, you're going to be visiting each of its left and right children, right? So how are we figuring out if whatever node we're currently on is the last element? That's one more question we didn't talk about before, right? So when you add whatever you want to add to the queue, before the start, like when you're at this point, before you even get into this loop, this would be the exact number of elements that's there on each of those levels, right? Initially, you see there's just one element on the first level, which is like if you take the size of the queue at this point, when you just have the first one, then your size would be 1, right? So okay, awesome. So what do we do now? We loop in terms of the size, right? If you have 2 and 3 for this one, right, your size is going to be 2. And then your next level, if you had left children for the nodes 2 and 3, then the last level would have had 4 elements. So your queue at this point will always have whatever is the true size of that level, it's going to have that. And I really, really wish I had we had more sessions for this one. Maybe we could think about it later. So great. The first one, we have 1, right? And what do we, once we get into this loop, the first thing we're going to do is we're going to pop off from your left. So the first time you have 1 in it, so you're going to pop that, and then pop that from the queue, and then you're going to check if that 1 is the last element, right? How do you check if it's the last element? You have a position over here. You have your index over here on top, which also acts like a counter. But yeah. So if your I equals size minus 1, size is the length of your queue at the moment. The length of your queue when you had only 1 there was just 1, right? There's just 1 element in the queue, and that is literally the last element anyway within that level. So you're going to, if you find that the position or the counter or whatever you're at is the last element this way, then you would append that node's value. You're not going to append, they're not asking you to append the whole node. Remember, a node has a value and then a left and a right child. This is a tree node, right? So it's going to have 3 pieces of information. First thing, we check the value. We checked if it's the last element, or we added that into our result if it is. And if you have a left node, a left child for the node, then you append it to the queue. If you have a right one, you append it, right child, you append it to the queue. And now what do you have in your queue? You would have 2 and 3, basically. Initially you had 1, next you have 2 and 3. Right? So, okay, great. Again, we come back to this. We come back to calculating size. We have 2 and 3 now. We're calculating the size. What is the size? It's 2, right? Again, we're going to be looping into that, right? You're going to pop out 2 first because 2 is in the leftmost in the queue. You're going to pop left. And if it's a stack, you'll just pop you just pop. If you because a stack is a last in first out kind of thing, right? So if you pop in general from an array, you're just going to get the last element, but you need the first element in this case. You could also use a dequeue here in this case, and I think it has a method called pop left, which is literally going to pop, which literally works like a queue. So awesome. So 2 and 3, and you're going to pop out 2. Now you're going to check, is 2 the last element? What is your I currently? And what your I is going to be 0, right? In this case, it's going to be 0. And your size currently is, your size minus 1 is going to be 1, right? Because you have 2 elements, 2 minus 1 is 1. But yeah, so your and because we're starting from 0, you could still start your range from 1 and then go up until up until size plus 1, which would just do 1 and 2. Anyway, going deeper there, should not do that. So once you take out 2, check its children, you add it again, and then you still haven't finished. You won't go back to size here because you still haven't finished visiting 3. So you'd again go into 3, and then you would pop that out from the queue, right? And then you'd get 3, and then you'll check if it's the last element, and then you'll append whatever is there in your tree. So currently your queue will have and this loop, your queue is going to have 5 and 4, right? Because that's the last layer. And this for loop will stop now because obviously like you've reached your range, so you're not going to iterate after that. You'd again calculate your size. Your size is going to be 2, and then you're going to do the same thing again. This time there's no like left or right children for either of it. So you're just going to see whichever is the last element, or the last your last element in the level, rightmost element in the level, and then you're going to append it to your result, and then finally you return result. So yeah, that's it for this one. For actually I'm doing pretty good on time there. Thought we'd be going over, but I'm trying to see if there's okay. So far we two questions, right? We saw 2 of this. The first one was validate binary search tree, and then the second was binary tree right side view. Both of it fun questions, really fun questions. You should probably like look at them separately. These are marked medium, and like it's a bit, if you do it recursively, I feel like it's a medium or a hard, but like if you look at it iteratively, I definitely feel like, okay, like if you, and I'm not saying it in any like, oh, okay, like it's just all like, pretty simple to do. Like I'm not one of those people, but like I've actually, when I did trees for like a whole week, this was really simple to see. And I feel like that's going to be the same thing with all of you as well. So yeah, let's look at the next one, right? This is something that you'll see a lot. Okay. Yeah, I definitely, I think I shouldn't be doing like fast-paced ones because like I'm not good at explaining things like like summarizing things like that. But yeah, definitely, like I think it may help if you revisit them. So yeah. Okay, so fast and slow pointers, slow and fast pointers. Yeah. What are these, right? You may have seen them somewhere here and there, but they're mostly like from what I see, they've mostly been used within linked lists and within like if you're trying to find like a duplicate of an array or something, like what is a duplicate element or something like that. What is the actual idea here? Like you have 2 pointers, right? Just they're slow and fast, right? They both start at the same position and then they move at different speeds. It's not like one has a head start over the other one. They're just, I think this is called, what is that? Yeah, Floyd's tortoise and hare problem. I think this is an algorithm that many people like they've mentioned, but I just call it fast and slow pointers. I think many people do, but okay, they start at the same position and then they move at different speeds. The fast pointer, depending on what you want, can move like 1 step, 2 steps, like faster than slow. And then naturally, depending on the problem you're doing, if you're doing a linked list cycle kind of problem, which we're going to see today, naturally they'll come to a point where the fast meets up with the slow pointer. It just happens because like, when you do these iterations one by one and see why these things are the way they are, they literally matched up. So you would always find that these 2 meet at some point. And this meeting, it could be like based on your problem, you could either like discover a cycle within it, or like you could find out like a duplicate element within the array, or like you could basically figure out some piece of information, because fast met up with slow in some way. You'd figure out some kind of information, but it really depends on your problem and where you're applying it to, right? Like, yeah. So where do you generally do stuff like this? When you need to basically, if you have a data structure and you're going to traverse it, and you like, if you're going to try to find an intersection or some kind of, if you're going to make some kind of inference based on these two pointers meeting, that kind of way, when you see it like that, like a loop sort of thing, then it's best to use these pointers. So that is like the general, like, overall idea of it. Again, I'm really sorry for like pounding everything in at the same time, but this is also a really fun question. It's called linked list cycle. Okay, so what is this specific question, right? What are we talking about here? You have, obviously, whenever you're given a linked list problem or something like that, you would be given the head node of the linked list. If you have a tree, you would be given the root node, so on and so forth. So you're given the head of the linked list, and you have to traverse through it, right? You have to determine if that linked list has a cycle in it. What does this cycle mean? There's a cycle in a linked list if there's some node within the list that can be reached again by continuously following the next pointer. So in this example, 3, 2, 0, -4, and then you loop back to 2, right? If you keep following, and for a linked list node, just like in a tree, you have a value, you have a left node, and then you have a left child and a right child, 3 pieces of information within a single node in a tree. So within a single node in a linked list, a singly linked list in this case, what pieces of information do you have? You would have your value, and then you'd have your next pointer, and then your next pointer is going to point to the next, basically the next node, and that node would have a value and next pointer. Okay, like, you get the data structure, right? So awesome. So why did I get to that? I'm thinking. Yeah, okay. So when I just looked at this problem, I was thinking about that. So your three's next is 2, 2's next is 0, 0's next is -4, and -4's next would be 2. And why, like, how is this actually like internally done? That's what they've mentioned here. Internally, position, POS, is used to denote the index of the node that tail's next pointer is connected to. Note that position is not passed as a parameter. Very helpful, but thank you for that. So it's just helpful to understand how they've done this, right? So what they're saying is, you already, in this case, for this linked list, your position is going to be 1. And why 1? This is 0, this is 1. Your tail pointer, it's pointing to 1, right? So that's what they mean there. And then again, the last one is if it return true, if there's a cycle in the linked list, otherwise return false. Okay, cool. In this example, you have this list, linked list, singly linked list, 3, 2, 0, and -4. And then your cycle, you're seeing it in here, like it's at index 1. So in this question, you're not gonna find out. I think there's a variation of this question where you have to find out exactly where this thing happens, this cycle happens. I think that's a good follow-up to this question. But for this question, you just have to figure out, like, do we have a cycle or not, right? So let's just simplify whatever's there. You have a linked list, like you have a head for the linked list, and then you have a position that indicates where the tail is connected to the cycle. We're not given that as a parameter. And then if cycle, return true, otherwise false. How do you actually figure out if this has a cycle, right? Okay. Yeah, so basically I'm going to go into LeetCode directly for this. I've put up this, like Karen's also put it up in chat so that we could all get to this. But yeah, it's so strange that we've done 7 sessions, but I've never really like been on a LeetCode screen within a session. Like it's really strange, like to see this screen here. But yeah, so to put this in a REPL, like we could create like we could create these list nodes. You could create your own linked list data structure within it and then like link it. But I wanted this particular solution to be as is. Oh, okay. Let's see. I'm going to do this. So this is what I posted there anyway. But what should we find out, right? You should just figure out if there's a cycle or not. Okay. So basically, in terms of fast and slow pointers, you're just going to begin with 2 pointers. One at both of them at the start, which is at the head, right? And then you're going to be moving them in terms of like, one is just going to move to the slow pointer is just going to move to the next node and the next node and the next node, one by one in each iteration. And then the fast pointer, we're going to make it move twice. Like we're going to do something like it jumping an extra step then slow. So if your fast pointer begins at 3, you're going to want to move it to 0 next. And then from here, from -4, it'll jump back to 2, right? Like you're going to do it in steps of 2, and then slow, you're going to do it in steps of 1, right? So at some point, if you let's actually see how they may meet, right? If you're starting from here 3, actually, I think I'm gonna, yeah, I'll probably just explain it like instead of writing it out, because I want to be able to see both of it at the same time. So if your slow pointer is starting from 3 and then your fast is also starting from there, the first time your slow is going to be 3, fast is going to be fast and slow are here. The next iteration, your slow is going to be at 2, and then your fast pointer is going to be at -4, and then your slow pointer is going to be at 0, and then your fast pointer is going to be at 0 again. If you notice, because there's like 2 jumps, right? It's going to catch up to it. So when it catches up, then if it catches up, then you know for sure that there's a cycle somewhere, right? If it isn't, then it won't catch up, right? There's no way for it to, if -4 didn't really have a cycle, your fast pointer would become none when it reaches it. When you try to get to like, oh, -4 is next. What's -4 is next? It's none. If it isn't, if there isn't a cycle, then it should be directly none. But there is a cycle in this case, so they catch up. And then if they catch up, and if both the slow and fast pointers point to the same thing, then you return true right away. If they don't anywhere in this whole process, then you just return false, right? So that's simple enough. That's it. There's no like additional stuff here. And this is an easy problem, as you can see, and it's pretty fun to do. Yeah. Okay. Impromptu quick coding thing, right? What are we initially going to do? Right, we're going to do slow and fast pointers. So we're going to start off with, I can't type, slow and then fast. Both of it, they should point to head. And then moving my chair a little bit. Okay, so now what are we going to do, right? While this while condition is really important, because suppose you have just, I don't know, like you just have one element, right? In this case, you just have one element. If the first time both your slow and fast pointers are going to point to this one, and then the next time your fast is going to be none, right? In that case, there's no cycle here anyway. So you would definitely make sure that there are at least 2 elements here, right? To at least try to at least see if there's a cycle or not. So that's what we're going to check initially. So while while fast or fasts next, right? Within this, what do we do now? Nothing. We're just going to iterate. That's it. Like we're just going to traverse. So we're going to set our slow to slows next, and then our fast to fasts next, 2 steps. So next. And we can do that in a link. I thought it was super weird when the first time when like I was looking at it in school, I was like, wait, how is this possible? But yeah, it's possible. Because they're all linked together, right? You can easily access, like if you do, if you know the length of a linked list, you're going to access all the way till the end if you know how many jumps you have to make. So something like that. What is our condition? Like what is the thing that we want to figure out? When do we know that we have a cycle? Like have a, my gosh, cycle. Right? If our slow equals fast, then yeah. So there are two in a node. If you see here, this is the list nodes definition. In general, in a linked list, if you take any node, you'll have two pieces of information. The first information is going to be the value at that node, and then the second piece of information is what the position of the next node that this node is connected to. So this is a very like anywhere you create like if you're learning this data structure, I would definitely suggest, if you're starting to like get into data structures, before you, like if you haven't seen the data structures before, make sure to implement all of them separately. Like if you're doing like, try to implement the linked list, all of the functions within it. So if you're taking, I'm just going to finish this and then ramble on, but because this is our like condition, right? So but basically the next pointer is the next node this pointer points to. I'm going to like get into that, what I was trying to say before, in just a second. So if your slow equals fast, then you return true. You could do it in one line, but yeah. Otherwise, like if nothing catches up, or there's no chance of this happening, then you return false at the end. And again, this is just going to be like O of n in terms of time, because you're going to be moving all the way. Like you basically need to go until your tail pointer, which is connected to your, actually, yeah, it actually depends. You may have to like iterate through every single thing, and like every single node within your linked list, and you like in terms of like space, you just store like the current node, or like whichever node you're at. There's just 2 pointers. There's nothing much to think about there. But this is, just gonna do that. So this is it. Like I used to do, like I'm just gonna run it once to see if it works, or if I made like a small mistake or something. Yeah, these are all my embarrassing attempts at this. I think like, 2020. My gosh, I think there are some problems. Like I had like a huge list, and like I think it was like 2019 or something, and I've made like super embarrassing mistakes. But what did I do here? Wow. Huh. Fast next. I think, oh my gosh. Okay, I should have done fasts next and fasts next. See, I did it again. My gosh, why did I do that? Hopefully this works. Let's see. Let's first change it in our thing here, right? You can change your like input and output, or like you can change your input here to test. Right, this is a custom test case. Let's see what happens now. Wow, my gosh, I have no idea what I'm doing here. You have slow, and then you have slows next, you have fast, and then you have fasts next. Maybe it should be, oh, okay. I'm gonna try one more. This is even more embarrassing to do it like this, but let's see. Right, we need to. I'm gonna try a couple of things. Right,
I have a suggestion. I think it
go
can
ahead.
read the first one. The first one is non-type. So yes, promises is an attribute. I think it's something has to do with like when it's none. Is it
Yeah. Um,
is there any way we can do like a skip
we could
none or
basically. I feel like we just have to change the we just have to make sure that there's the fast and there's a fast next. Just change it to an and. But let's try it out. Or maybe we could we could check out the none stuff too. Wow. Okay. It seems to have worked. Let's run it then. Right. I could yeah, I don't, this problem it doesn't really that dummy that sorry that the I actually have no other way to say it other than dummy head as well. But like those problems, there's something called add two numbers, and like those problems they actually require it. This one I don't think it does. I don't know. I'm just gonna try to submit it. Huh, okay. Yeah, it's just that condition that I missed there. But you could do it with a dummy head. But yeah, I think this is simple enough as is. Just carry on with it, and yeah. So this is it for the coding portion. And with that, we may have like, if anybody has a couple more questions, we could do that. Or we could, like, if you have more questions, you could ask it in the channel and like tag me, Karen, Stephanie. We could all jump in and answer. But yeah.
Now is definitely a good time for those of you who had a question and we were too busy, like we couldn't answer you properly. Please ask again. We love questions. That's why that shows you guys are learning. That's why we love it. So I think we have a question about the last line of the
Is
while
this a,
statement.
yeah, I'm wondering if this is the one that you're mentioning, Promise, or the previous problem, or this, or the linked list problem.
Okay, let me. I think it might be the same approach. The while, if you only did a channel, maybe you can correct me if I'm wrong. I'm trying to
No, you're
learn
gonna be
here.
perfect.
So the while queue and the while fast, that's the exact same thing. Basically, the while fast is like a short form of while fast equal to true. So if it's a false on a type, it's not gonna process anything. That's the condition there. So the linked list, yeah, I think that's the while statement.
Yeah.
So
yeah.
yes,
So yeah.
Go ahead. Sorry.
No, you go ahead, Kevin.
That's all I have actually.
Okay. Yeah. So basically here, what I was saying initially is, if you have like if you have, actually, if you're doing, let's see, let's look at this problem here, right? So in here, if you start off with the first element, like that's going to be your fast is going to be true nonetheless, no matter what, in this entire case. It's weird because like I feel like it may go on within like an infinite loop or something like that, right? But if you don't have a cycle, if you have a cycle, at some point you're just going to return true, right? If you don't have a cycle, then there would be, I'm getting to that in just a second. So if you don't have a cycle, then at some point your fast node is going to be, if it was -4, right? If it was -4, it's going to be none next, right? Because -4's next is going to be none. Like there's no like, actually, oh, okay. If you're at, let's see, if you're at 0, right? Supposing at some point you reach 0, right? And your slope pointer is not there, it's somewhere else. Let's assume it's in 2 or something. If your fast pointer is in 0, now you have 2 things to worry about. You won't be able to, like, once you set it to 0, and then like you set it to 0 here, and then you come back to this loop, right? Before you even get into like your all of this stuff, you would check if there's going to be a next, or like if you have, maybe if you're in -4 or something, if you look at the next element for it, it's going to be none anyway. So you make that check beforehand, like you're going to check it here, and then if you reach outside of -4, then your fast itself is going to be none. There's going to be some points where you're, where you're fast, and like your fasts next, they're either one of them or both of them are going to be none somewhere. So just making sure that you're, like you're able to traverse. That's basically why that condition is there. I think like you could also, I think if you modify it, right now I'm not able to think about it, but if you modify it a little bit more, you could also try to check like fasts next, and like you could basically, however you design your solution, you could check it that way from what I was doing for some time. This is basically what I've been doing. If it doesn't make more sense, then maybe like tag me again in the channel, and then like we'll go over it again. And there was another question. Okay, how many types of algorithms do we have? Like, we can list data structures? Can we list algorithm list of patterns? This is a bit of a tricky like question, I think, because there are certain things that we say that, okay, these are actual patterns. If you say 2 pointers, 2 pointers is not really like it's also an algorithm, but it's not like one of those prescribed algorithms. If you say, oh, okay, backtracking is actually an algorithm, right? It's also a pattern. Like, so maybe like the way I think about it, I think, is this particular thing, whatever I'm choosing, is it something standardized? Like is it within like a book, or like do people talk about it in terms of it being an algorithm outside of problem solving? Then like, that would be both a pattern and an algorithm. Like, other than that, these other things, I think there are a couple of them. I tried to cover a couple of them here. There's so many more, like the dummy node stuff. Like, if you take that question is called add 2 numbers, I think. So if you look at that, you'd understand why we use that particular pattern that way. So patterns, I would say there are a lot of them. It depends on how you look at them or how it appeals to you. Like, for me, this is a pattern. For me, many things are patterns. It depends on how you compartmentalize it in your mind. That's what I would say. But there are some like patterns that we've been discussing here on the study group. So yeah, I'm not sure if I gave like a concise answer or not, but yeah, I guess just I would say there are a couple of super important ones that you have to know. And I think, except for dynamic programming, which like I'll just introduce like a slide for it. The next week is going to be mostly just like resources for things, like just like a recap of everything. We're not going to be like doing like actual problems next week because it's like a wrap up for the series. So we're just going to be, looking at resources. So like I'll try to like compile a list of things that I think were important to me and like are important in general from what I've been seeing. So yeah, that's I'll do that for the next session. But there are about some of them. Yeah. I think. Oh, okay. I'm looking at Karen's answer. Thanks, Karen. I feel like when somebody's if you're doing an assessment or something like that, you don't have to worry, like an online assessment, like they give you a hacker rank, you don't have to worry about building anything out. They're going to be doing most of it. Like you just have to fill out that function. Like that's about it. If you're doing like an actual interview, it really depends on your interviewer. Like personally, if your company, if that company, wherever you're going to be interviewing at, if they're doing like a coder pad or like a hacker rank where there's nothing on the screen, you have to fill everything out, then that's on us. Sometimes they would put in like boilerplate, like if I definitely feel like for actually difficult problems, they would have in like the data structures and like whatever they'd have like examples. From what I've seen, they've had examples of like the code of like your input, but they would definitely not make us do all of that in an interview setting. They would have the list nodes and like those declarations beforehand so that we can just jump into our portion. Because if they're doing like a coder pad, then then they usually fill everything out and then leave out whatever you have to fill, right? So yeah. So for the
And I'm more Yu Jong, sorry if I kind of attack your question because your question kind of remind me of one of my personal experience. It was kind of stupid. I actually was asked. I was in a technical interview. I have no background on these like algorithm structures. So I was actually, they were asking me a very simple question. And then the first thing I thought of, it was very interestingly, like I was using a library. And it was kind of sad because like the question, basically what they want is to see us how to solve the problems instead of what library to use. I know in data science and data analytics, there's a lot of like library, like what kind of library, what use this. It's for convenience purpose, but when you go to interview, it's not about how much you know about like a specific library.
yeah
It's really about how do you solve the problem. So I really want to bring that out so that like no one like had like embarrassing moment of mine. So yeah, so I think it's good. It's good to practice like a lot of like how to solve them
yeah
on your
definitely.
own first. And that, you know, at the same time, like if like you get to work or something, definitely use a library. And I think a lot of like algorithm actually the I think is the code itself is very simple. Like you can see kind of like it's, you know, like it's like less than like 20 lines of code. But then like the story behind it, the structure behind it is way more than like that what you see right there. So that's what we want to more probably
Yeah,
practice on, like for myself as well.
yeah, definitely. Like if they ask us to, if they ask you to do it, then you need to do it. Here, even in here, like you never, like if you notice, we just use like basic like things. We don't even try to like use any of those like complex things. And also like one more thing that I've always wanted to mention, it's like a random thing that popped up in my head. And we're also at time. Ooh, okay, I'll just quickly like wrap up and then we'll just talk about that one second.
We always like have a long discussion at the end. Sorry,
Yeah,
Stephanie.
we're super interested to talk. Like, yeah. Yeah, so these are some of the links that we've always had before. This time, like we don't have much in the REPL. Like I just started to stub out this code in the REPL, but then I realized, okay, like, I want to do it in LeetCode so that like once I finish all of that, then I can create like the list nodes and the linked list methods and stuff. You have to do all of that to be able to do it. And so that part of it, the bonus patterns part of it, just other than that, look at everything else. Just that part, I'm gonna have to take some time and change it, or maybe remove it or something. Depends on how we do the next session. But yeah, that's a REPL link. And then for mock interviews, now PRAMP, I'm not even sure. Like, I think there's another company called Exponent. They bought them, I think, or interview.io. I don't know. There's so many out there. I think somebody bought them, and I'm not sure if they're free anymore, but definitely worth looking at it. And definitely try to do LeetCode contests, even if you don't even do one question. Like, just going out there and like in that pressure situation, like, if you that stimulates, like, why do I keep saying stimulates, that sort of, I don't know if it's emulates or simulates. I'm gonna stop it there. But that sort of gives you the feel of an actual like online assessment situation. So try to do that. And then our last session, that's on February 17th. A lot of just talking, resources sharing, wrapping up, that kind of thing. But yeah, the previous sessions, like, we've shared it many times. They're there all over. And yeah, join us on social media as well. And upcoming sessions, there's introduction to Qt. That's amazing. We've Karen, have you had one session before this for Qt, or two?
I joined one officially. The second
Awesome.
one, like, it's been amazing. Yeah. So if any of you interested in like making like making a widget, I think I stated it wrong, right? Like making like a layout, like a mini application. This is a fun session to join. So we are in our third, I think it's the third session, like they're going through the third session. Jessica is the presenter. She's amazing. So please join her. And if you have any, like, we also have any, it's Ashika coming. Ashika is amazing, amazing person. So please join her in the AMA series and, like, share. Like, she's an amazing person. She has a lot to share. I love talking to her. So please join her. And then, like, she's very encouraging as well. And we also have a co-series with the data science track, which almost everyone here pretty much interested in, on machine learning study group. So if you're like, definitely sign up. I'm not sure whether you're interested or not. It's good to know. So sign up. Just sign up. Yep. So remember to follow us on social media. We're on Twitter. We're on LinkedIn. We're on Instagram. And we remember to join us on Slack as well, for us that if you ask any questions. And we will see you next week.
Awesome. Thank you so much, everybody.
Bye, everyone.